Hello guys, welcome to video lecture series on assignment questions. In this video we will be learning about the answer for third question for 3A and 3B. Coming to 3A, question mentioned by me is explain link power budget with an example. In order to calculate link power budget, we will be calculating losses that occur in the optical system. So first point we have written is for optimizing link power budget, an optical power loss model is to be studied as shown in the following figure. An optical power loss model. That means we are considering a model where optical power will be lost. Okay. And we will be assuming all the possible losses in optical system. Coming to this system, the first device that you are finding is transmitter. Transmitter is connected to a connector. Using the connector, an optical fiber is connected to the transmitter. Then comes different splices. And then at the other end, you will be finding one more connector, which is used to connect this fiber with receiver. So here at the connector, we are getting a loss and it is estimated as LC. At this place, at each place, we are getting a loss and it is estimated to be L suffix SP. Now between these splices, there is a fiber and this fiber will have attenuation and it is estimated or denoted using alpha suffix F. Coming to this, next point what we have written is let LC denote the losses occur at the connector and LSP denote the losses occur at the splices. Alpha F denote the losses occurring at the fiber. Now, all the losses from source to detector comprises total loss. Here you can observe from the source to the detector, all the losses are going to constitute a total value and it is considered as total loss or power lost. Link power margin considers the losses due to component aging and temperature fluctuations. In this system, there will be variations in the temperature. Due to temperature variations, there will be some more losses. And then after some years after laying this fiber, there is an extra factor known as aging, due to which components may get damaged or wear and tear may occur in the system as the time is progressing. So it is known as aging. So in these two cases, due to temperature and aging, let us assume that there is a loss of 6 to 8 dB and it is known as link margin or system margin. Usually a link margin of 6 to 8 dB is considered while estimating link power budget. Total optical loss. Now, total optical loss is calculated as losses occurring at the connector, splice here, and then fiber attenuation. Then comes system margin. All these losses are added together to have total losses. It is given as PT is equal to 2LC plus alpha F into L plus N times alpha SP plus your system margin, where L is the transmission distance. Okay, alpha F is per 1 kilometer. If there is L kilometers, the fiber has been laid, then it is considered as L. So it is multiplied with alpha F in order to get the total attenuation for the complete length. Now in the question I have asked for an example. Let us consider an example. Design an optical fiber link for transmitting 15 MB per second. This is the data rate of data for a distance of 4 kilometer with bit error rate of 10 power minus 9. This is the bit error rate. Now coming to the solution, if you need to transfer a data of data rate 15 MB per second for a distance of 4 kilometers, then the bandwidth required is estimated as bandwidth into length. For the complete transmission, you require total data rate to be considered as 60 MB per second for all the this much of data is required to be transmitted for the complete length of 4 kilometers. Now selecting an optical source. Let us assume that we have considered an optical source that is having 820 nanometers, that is providing a wavelength of 820 nanometers for short distances. LED generates my 10 dBm optical power, which is generating an optical power of 10 dBm. Now coming to the detector, a detector is selected such that it is reliable, that is pin detector, pin diode has 50 dBm sensitivity. It has a sensitivity of 50 dBm. Selection of optical fiber. Let us assume that an optical fiber is selected and it is step index multimode fiber. The fiber has a bandwidth length product. In the same way, we have a bandwidth and length product of 100 Mbps per kilometer. Okay. Now link power budget. How to calculate this link power budget? They have, let us assume that splicing loss is 0.5 dB per slice. Connector loss is 1.5 dB at connector, and the system link margin is 8 dB as it have not given. Fiber attenuation is alpha f is equal to 6 dB per kilometer. Now to calculate the total loss, what we need to do is we need to add the all losses that have occurred. Here we are not adding splicing loss because we haven't considered any number of splices. That means we have taken a 4 kilometer straight wire, so there is no loss due to splicing. So now this is a simple mathematical equation where we are substituting these values and calculating the total loss that have occurred. Now we need to check for one condition. This is the total power loss that is occurring in the system if we have used these components. But we need to check whether the system is supporting this much of loss. If the loss system supports is very less, then we will be losing some signal. So what is the maximum allowable system loss? How much loss can a system allow? It is estimated using P max is equal to output optical source output power minus optical receiver sensitivity. Thus power which is coming outside minus sensitivity of the receiver. Optical source output power is minus 10 dBm while the receiver sensitivity is minus 50 dBm. So it can sustain a loss of 40 dBm. Here the loss occurred is 35. So as this loss is within the range, you can take it. Since actual losses in the system are less than allowable losses, hence the system is functional. You can use the system. Now coming to the other question, explain the working principle of distributed feedback laser diode. It is shortly abbreviated as DFB. In distributed feedback laser diode, the lasing action, what is mean by lasing action? The process of providing light output, all the action which is taken place in order to create a light signal is obtained by periodic variations of refractive index along the longitudinal dimension of the diode. That means in this dimension, we are changing refractive indices. Due to this change in refractive indices, a lasing action is taking place, which is providing an output. The following figure shows the distributed feedback laser diode structure. Here you can observe these are the gratings for variation of refractive index where we are changing refractive indices, different refractive indices. And then comes optical confinement layers. Your light active element will be present in this layer. Between these two, your active element will be present, and from there you will be generating an optical signal, and that optical signal will come out in this way. The electromagnetic wave propagating in longitudinal direction is expressed as, so the light ray which is propagating is electromagnetic in nature, and it is represented in terms of intensity of light I of Z into your components, other components, that is frequency, time, phase constant, and the distance it need to cover. It is represented as e power j omega t minus beta z. Now, where I of Z is optical field intensity, as we have seen in the formula, I of Z is electromagnetic field that is coming out of the light depends upon optical field intensity. Then omega is frequency, beta is phase constant. Now coming to the basic equation, fundamental expression for lasing in Fabry-Perot cavity is given by, it is expressed as I of Z is equal to I of 0 e power gamma g hv. Hv is nothing but your energy, and this is alpha hv into Z. Coming to this equation that is in your Fabry-Perot cavity, in a general cavity, this is gain which is occurring, this GH is gain which is occurring, this GH is gain that is occurring, and the alpha H of V is loss. That is gain which is occurring in as a function of energy and losses that are occurring as a function of energy. After finding the difference, remaining energy is considered to be your optical intensity. This is when initially, this is I of 0 is at the initial point. This is variation with respect to Z, that is as the distance is traveling. Gamma is the optical field confinement factor of, or the fraction of optical power in the active layer. This is the optical power which is generated in the active layer, and this depends on gain and the losses that are occurring. Is the effective absorption coefficient of the material, losses due to absorption of the material. G is the gain coefficient, HV is the photon energy, Z is the distance traversed along the lasing cavity. This is the distance covered along the cavity. Now, lasing here, Lasing occurs when gain of modes exceed above optical loss during one round trip through the cavity, that is Z is equal to 12. So lasing, light amplification occurs. Lasing means light amplification occurs when gain of modes exceeds above optical loss. Gain occurs, gain is more than, if your gain is more than the loss, then we can say there is some amplification has occurred during one round trip through the cavity. That is, for a round trip, what do we mean is as it traveled the complete length of the cavity. If R1 and R2 are the mirror reflectives of the two ends of the laser diode. In the laser diode, we are placing reflective mirrors at this end and this end. As this light ray is being transmitted, in order to reflect this, we are placing some mirrors and they are indicated as reflectivities as R1 and R2. Now the expression for lasing is modified as, now from the previous equation, we can change this to, if it has completed a distance of 2L, if it has completed a distance of 2L, from this location, it has completed a distance of 12. So Z is replaced by 12 and remaining equation is as it is. The condition for lasing threshold is given as I of 2L is equal to I of 0. Okay. For phase, when the phase is noted as 1, if this is considered to be 1, then we are considering this two are equal. If there is any phase change, then it is going to be represented in this way. Optical gain at threshold is equal to total loss in the cavity. For a phase of 1, now we are assuming some conditions where optical gain is equal to total loss in the cavity. If the gain occurred is equal to loss in the cavity, this and this is equal, it becomes 0, e power 0 becomes 1. Okay. This is becomes, this and this are equal, then it becomes 0, e power 0 is equal to 1, then these two will be equal. Okay. Now the lasing expression is reduced to, now that expression has been changed to gain is equal to attenuation that has occurred. That is what we have said, attenuation that has occurred is equal to gain. Then this attenuation is noted as attenuation due to those reflections from one end to other end, and then the attenuation of the material. So these two are, end attenuation is nothing but the attenuation which is due to the mirrors which are causing. So these two attenuations are equal to the gain. In order to have amplitudes equal, A end is a mirror loss in lasing cavity. An important condition for lasing to occur is that gain should be greater than threshold gain. Okay, that means this is the threshold gain. If this threshold gain is equal to alpha, it is okay. The original gain should be more. Original gain occurs due to multiplication of your electron charge carriers. Okay.